executable. It is not something that it does when the program runs. It's something that is done as you are constructing the thing that's actually going to be loaded in and executed. All it does, it basically sets aside this memory location and puts the value there. Let's see. Let's write. That's probably the best way to illustrate what goes on here. Let's, yeah.
I'm assuming I know the answer already. But on the assignment, you want us to set aside 10 blocks of memory. Can we just do it this way and assign?
Now,
or do you want us to use dot block?
Be careful. The dot fill sets one memory location. So if you want to set aside 10 for an array, using fill, you've got to have 10 of them.
In a row.
So what can you use?
Or you can use the block word. Okay. Block word 10 sets aside 10 memory locations. Does not initialize.
So how do you put the values into that block?
If you're going to use block word, then somewhere in your program you're going to put numbers in there. Okay?
So for when we test our program, can we do the dot fills and then when we turn it in, we just use the block word?
Yeah.
Does it matter?
Yeah.
Yeah, when putting like values straight into the code, do we need to separate them by comma or can we just go to a new line?
What do you mean?
Like if we're putting values into the block word in 10 locations, say we want a variable, string, string 1, string 2. Do we need to separate those with a comma or?
The value that you put on block word is the number of locations, not the contents of those locations.
Okay.
That's right.
And do those?
Block word does not allow you to put things into those locations.
Okay, so then there's no comma needed.
It would have to be done from within the program someplace.
Okay.
So you have to know what the memory location is, like if you were putting in the first one, like you use the block word and then you put in the first one, or you want to put in the first value, you have to know what the memory location is that the block word.
Yeah, typically you'll put a label on it.
Yeah. I started with block.
Let's write a little program here. I think it'll straighten things out a lot.
It's getting easier. At first I was trying to find the crap.
Okay, we'll start at the typical place. Let's see. Load, register 0, X, add, okay, using the dot fill, here, I'm just going to put a 0 in there. Now, here's what happens. this is, of course, at location 3,000. This is 1, 2, 3, 4, 5, 6. Oh, wait a minute. That thing's messed up. I'm off by 1 on all my counts there. Because these things are not instructions. They do not occupy space in my memory. So, let's see what goes into these actual memory locations. What do they look like? This is kind of why we fuss so much about writing programs actually in binary, because it does help you see how all these things work. The load instruction, 0010, we're using register 0, and then we've got an offset. The offset is the distance from here, the next instruction to here, so it's a 4. So it's 100, and we've got 9 bits, 1, 2, 3, 4, 8, 9. Okay,
Wait,
that's
so
what
you're
that
going from
instruction looks
301
like.
to 305 or to 304?
Yeah, what?
Are you trying to?
Oh, yeah, I did go 5, didn't I? So, yeah, okay, thank you. 011. It's from here to here, because I'm trying to load X. Now, my add instruction, is 1. Using register 0 in both cases. So now I've got a 6-bit here, 2, 3, 4, 5, 1. I'm not lining up very well here, sorry. Now 3002 is a store instruction, which is code 3. Again, we're storing register 0. Now my offset here, I'm storing at Y. Next instruction is 3. There's a difference of 2. 3, 4, 5, 6, 7, 8, 9. Offset of 2. The halt instruction, remember, is a trap. The next 4 bits are all zeros, and then the trap is a 2-5. Now what goes in this location? All that goes in there is this value. And then in this location, since I've said zeros, okay, that's how the fill instruction works. It just tells the assembler when it's building this binary code, because remember, that's what's executed, not this. This isn't executed, this is. It says, put this in that memory location, wherever it falls in the system.
So, I just want to clarify something. If the label, or if your location there is out of range, if you're more than your offset 5 or whatever, or 9.
Can handle.
Yeah, you have to use an LDI instruction, right?
Yeah, yeah, you're gonna have to do some fussing with it to
Right.
accomplish
Will
it.
the compiler tell you that it can't reach X or Y?
Yes, because
Yeah.
I tried it.
Sounds like a voice of experience there. Yeah, if you're out of range, it will tell you. Typically, typically the way to handle that is to use the LEA, the load effective address, and then use an offset from that.
What's the LDI, please? Don't remember that.
LDI? Okay, let's go over LDI one more time.
Thank you.
Remind you how that thing works. Well, let's see. Well, yeah. LDI has a register and an offset. What it does, it takes the contents of the register plus the offset that has been extended to the full 16 bits. And that gives an address. Now, up to this point, LD would move the contents of this location to the register. Okay, that's the way this thing worked. That's what we did there. Up to this point, it's identical, doing the same thing. Now, the thing that's different about LDI is it now takes the contents of this location, now used as an address. Oh boy. Trying to write some code to get some numbers up there to show exactly, well, we did it a lot with the, with what we were doing on Wednesday with the keyboard data register. Okay, let's go back over that. FFE0 and FFE2 are the appropriate register values. Here's what we did. FFE, it's FF0. FE02, that's where I'm off. Okay. I want to fetch the value from this location. Now, it's too far away for the offset. If I'm down around the 3,000s, figured out, get from 3,000 to 15,000, roughly 12,000 memory locations. I can't do that in 9 bits. I just can't. So there are a couple of ways you can do it. Let me show it without the LDI and then show you how that LDI comes in. I can do this. I can say load register 3 from the keyboard data register. Now that just loads this number into register 3. But this isn't my data. My data is out there at this memory location. Okay, well, I can say, use the load relative, LDR, register 0, I'll use register 3 with an offset of 0. Okay, that takes what's in register 3, which is this number, adds a 0 onto it, and then goes to that location in memory, which is way beyond what I can get with an offset, and copies it into register 0. Okay, you see how that works? I'm building an address that's way out of range of what I can do with an offset. That's what I'm doing. And I do it by having an address down here close by. This happens to be an address that I know. It's kind of hard to do sometimes within a program because you don't know where things are going to end up all the time. But I know this address, it's fixed, because the keyboard and the display status and data registers are always in the same place. So I can hard code that address in there. Then to work with it, I copy it into a register and then work with an offset from there. Now, let's see, to illustrate how this thing works. Well, this thing is going to, without knowing, well, I'll make up some numbers for the address. This is 0010, and then register 3, and then I've got an offset. Okay, made up, no particular significance. It's just that in what I'm going to do, I want to have that value, okay? I'm saying that's the offset from here to here. It's pretty big, so I've got a big program there. Okay, now, the idea behind the LDI, the load indirect, is that this becomes simply LDI register 3 KBDR. Does it as a single instruction. This becomes 1010 register 3, and then it'll have the same offset. 0011 01001. Okay, what does this do? It takes that offset, goes to that memory location, copies this into this register, then it uses this register as an address to get the actual data value to put into register 0. This does the same thing.
So the LDR is taking the, going to that address, adding the offset.
Well, no, this does not have this value associated with it in any way. That part doesn't translate over. But what it's doing, it goes to this memory location based on that offset, goes to this memory location, fetches this value, goes to that memory location, and then fetches the data. Okay, that's the indirect. We go directly from here to here, indirectly on one more step.
R3 then would hold the contents of what that address had. Is that,
At the end of either of these sequences, register 0.
or our register 0?
I want, on this one, I want register 0. At the end of either of these things, register 0 will contain what is in location FE02. Way out here someplace.
It will contain that content, that value that it holds.
Yeah. Okay, that helpful? See, it's a matter of this thing playing the role of a variable, but the contents of that variable is not the data that you want, it's the address of the data you want. What is that in C++? It's a pointer. This thing is a pointer. And that's what it's doing. Saying when I go to this location out of here, what I fetch out of there is not the value I want to put into register 0. I have to use another load to get to that. Well, we do it directly in one statement. We combine those two operations and avoid the use of register 3. That's another benefit of doing it in a single statement. We avoid the use of register 3 as an intermediate.
Does LDI work faster than LD, LDR?
Would it work faster than these two instructions?
Yeah.
Yes. Because you have, I think, just one less memory cycle. You only have to fetch one instruction. You're still going to go to this location and fetch this value out of it, and then another memory cycle to get to what you're looking for, but you have one less instruction to fetch. And so, yeah, there's a
You're
side
just
factor.
leaving out the part of putting it into register 3 and getting it out, right?
Yeah, and there is a little time saving there, but it's, compared to the memory cycles, it's minimal. It's hardly noticeable. When you start looking at time consumption on these things, far and away the majority of it is in memory references. The registers are really fast. Really fast. Okay. Let's see if we can get through this little project here in a few minutes. What we have left, about 20. Here's what we want to do. Create a decimal, and by that I mean base 10 integer from the keyboard to, what shall we say, register to. Okay, now what we have to do, basic idea here is that we need to loop through the characters entered. We have to strip off the ASCII code, and then we have to construct the integer. I'm going to, for the sake of this right now, say, first of all, I'm not gonna try and handle negatives. We'll just look at positive integers. Okay, let's see here what we can do with this. As my first step, I'm going to clear register 2. Then we will get a character. Then I've got to check that character and see if it's, see if I'm done. If not, let's see, I better specify where I'm going to put that. Into register 0. Strip off the ASCII. Multiply register 2 by 10. Add the new digit. And loop back up to here. And here, we'll just hold. Okay.
Why do you have to multiply by 10 again?
Because I'm putting in the digits from left to right. Okay, my first digit is a 1, my next digit is a 2. Well, I've got to multiply that 1 by 10 and then add the 2 in order to get 12.
Okay.
The next digit is 3, my number is 123, so I've got to multiply the 12 by 10, 120 plus the new 3.
Okay.
Okay? I'm just constructing this number left to right as the digits come in. Okay, so let's see. Let's begin here. Something. Want to clear register 2. Remember, that's a relatively easy process. You just do an AND against a 0. Check. That box is easy. Now, you recall that getting a character, what we have to do here is we have to wait on the keyboard until the slowpoke human out there actually presses a key. So we do this with a loop here. We'll just call it wait. And what we want to look at is that keyboard status register. That's the key. The keyboard status register, as we kind of indicated, has a lot of stuff in it, most of which we don't have to worry about. But the critical part of it is that the bit 15, the most significant bit, tells you whether or not a key has been pressed. So the way typically we handle this thing is that we do a load indirect in, we'll put it in register 1. Keyboard status register. Now, if there is a character out there in the data register waiting for us, that bit 15 will be set, which will make this number negative. So if this is either 0 or positive, I'm just going to sit here and wait. Okay, if you want to, some systems talk about that bit 15 in the status register as being a ready bit. It says there's a number ready for you. When it comes up to a 1, it says there's something out there that's ready, waiting for you. Okay, so as soon as we come out of this loop, it's because there's something there. So we'll load register 0 indirectly, keyboard data register. Now remember, you get one shot at that data register. You can't just go out and check it somehow and leave it there and say, well, I'll come back and get it in a while. When you look at it, that immediately clears that bit in the status register, and the keyboard is unlocked and ready for another key to be pressed, and if that next key is pressed before you go back and get that value, the one you wanted before is gone. Just got erased.
At that point where you do that next line, is that what you're saying, that happens?
No, this will not erase it. What will erase it is when the next key is pressed. And what this does is that it clears that ready bit and says, okay, you can press another key now, and when you do, it erases the old value out of the data register and replaces it with the new one. Now, typically, you'll have time to do a lot in between there, but it's best to move that thing out of there immediately and put it someplace where you can work with it.
Best to move it out of the status register or out of the data?
Out of the data register. It's movement out of the data register that clears the status register. This is what it says here. When a key on the keyboard is struck, the ASCII code for that key is loaded into the keyboard data register. And the electronic circuits associated with the keyboard automatically set the status register bit 15 to 1. When the LC3 reads the data register, the electronic circuits associated with the keyboard, not within the program, but with the keyboard, automatically clear status register bit 15, allowing another key to be struck.
What page was that you reading from there?
202 and 203.
Okay, thank you.
Okay, we just got our character in there. Now, we have to figure out how we can tell when we're done.
When the enter key is pressed?
We can use that as a signal. Yeah, there are a lot of different ways you can do it, but that's probably a pretty good one. Okay, so let's do it that way. If you look at the standard ASCII table, it's not the inside back cover, it's the page just opposite that. you'll find the carriage return, the ASCII code is 13 decimal, or a 0D hex. Yeah, there's the line feed. Typically, when you press the enter key, it generates a carriage return and a line feed operation. This goes back quite a ways on teletypes and other devices. Just a carriage return moves the print head back to the beginning of the line and gave you the option of overprinting a line, which we would do in those days to underline something. Go across and print characters, and then you could come back to the beginning of the line and go in and print underlined characters, basically on top of them, although they come out underneath.
So which one's the one that actually puts, that just moves you back? There's the carriage.
Carriage return. Line feed feeds you down to the next line. Okay, so it generates a carriage return line feed combination. Carriage return will be the first one. So what I have to do now is look at this thing and see if it's a D. Well, let's see. How can I do that? I have to do a subtract operation and see if the result is a 0. Okay, so now I need to get that D into memory. Let's see, we're using register 2, so we'll use register 3. We'll clear it, and then we'll add I'll just do it in decimal.
So
Put a
D,
13 in there.
D is the sign that the enter has been hit.
Yeah.
Okay.
Remember that when you press a key on the keyboard, when you press the number 2, it does not generate a 2. It generates a hex 3-2. That's the code, the character code. So we get this thing. Now we need to negate that and add a 1. Now that gives me the negative of that. Now I'll compare register 0 to that. And if the result is 0, I'm going to skip out.
What is that not doing?
In order to subtract,
Oh, it's flipping the bits.
That thing.
Sorry, I thought that, I mixed up with and. Like, that'll just give the same result.
Yeah.
Sorry.
yeah, I'm finding the negative of that
Sorry.
ASCII code so that I can subtract it and see if it's 0. Okay. Let's see. All of this stuff down in here is to generate the negative of the ASCII code for a carriage return.
Could you just load register 3 with -13?
Now what?
Could you just load register 3 with -15?
Possibly. Mm-hmm. Now, recognize that 13, how many bits do we have in that add instruction for an immediate operand? 5 bits. How many does it take me to represent 13? 4 of them. I'm getting close to the capacity. The biggest number you can put in there in immediate mode is 15. So you can't go much beyond that. Okay. So that's how I'm going to check to see if I'm done. Now, there are some other things we could do. We could, if you're gonna enter multiple values on one line, we could look for a comma. We could look for a space. If you're just gonna put white space between one number and the next one. See, there are a lot of possibilities here. Yeah, we're not gonna finish it. The ASCII code, we have to play with a little bit, because what I actually have to do is subtract 48 from what's in that register, and I can't do 48 as an immediate mode operand. Now, I could load it with 4 consecutive immediate mode adds, but there's probably a better way.
Before we check to see if enter was hit
Uh-huh.
with register 0, shouldn't we store it somewhere so that we don't,
It is stored. It's stored in register 0.
but then we're ending register 0 to, oh, okay, I'm sorry.
Yeah,
Right.
yeah, I'm adding it, and that's why I added it on to register 3,
Mhm.
so that I wouldn't change it. Yep. But now I'm about to change it. Okay. Here's the best way to handle that. Somewhere down here, as we get down to the end of our things, we've got our keyboard status register and our keyboard data register, where we've done a dot fill, FE00 for the status register and FE02. I'm going to put in here the actual ASCII code that's added on is 30. Now, what I'm actually going to store out here is the negative of that. Now, I can find that negative, subtract each of these digits from 15. Here we would get C. Now I would subtract this one from 16, but I can't do that, so it's FD0. Okay, now I will load, I can use register 3 now from ASCII, and then I will add register 3. Okay. That gets us down to this point. This one is easy. This one's going to take us a little bit. Yeah.
And then where you say load R3 from ASCII, ASCII's the pre-translated.
Yep. That's,
What's the
all these things will occur down here after my halt statement.
FFD 0?
See, I've got code
It's a
all the way
negative,
down through here, and here's my
30.
halt,
Oh, okay.
and there are my memory locations. Yeah. Okay. Well, I had hopes of getting through that today, but I guess not. We'll see you